बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश्रह सदरी व यस्सिर ली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Today we are going to cover Quantum Mechanics by Mark Beck, Chapter 1, 1.2 Linear Algebra, 1.2.1 Vectors and Basis Sets. We'll use what you already know about vectors from first year physics to develop a vocabulary for linear algebra, and then we'll build on that. We can express a vector A. We'll denote vectors with bold type that lives in xy plane as A is equal to ax ux plus ay uy, where ux and uy are dimensionless unit vectors that point in the positive x and y directions respectively. Ux is the dimensionless unit vector in x direction, uy is a dimensionless unit vector in y direction, and A is a vector. Any vector in the xy plane can be expressed by giving its components coordinates in the ux and uy direction. In equation 1.28, the components are ax and ay. The vectors ux and uy are called basis vector and they make up a basis set. This basis set contains two vectors because it is a 2D vector space. An n-dimensional vector space must have n basis vectors. A is a vector. A is equal to ax ux plus ay uy. Ux and uy are basis vector. Ax is the component in x direction. Ay is a component in y direction. Since we are considering only 2D vector space, we are only considering x and y components. In an n-dimensional vector space, we need n basis vectors. Vectors are a shorthand notation. The symbol A is a convenient way to denote the object that has multiple components. To specify the 2D vector A, we need to specify two numbers, its component AX and AY. Equation 1.28 is one particular notation for doing this, but there are others. For example, we could specify A as a row vector as shown in equation 1.29 or as a column vector as shown in equation 1.30. As long as we know what components of A are, we know what the vector A is. There are different notations for A, but they all represent the same vector. In terms of column vector, the basis vector in the xy plane can be written as ux is equal to column 1 0, uy is equal to column 0 1. The column vector equivalent of equation 1.28 is thus A is equal to ax ux plus ay uy. Since ux is equal to column 1 0 and uy is equal to column 0 1, we get ax in times column 1 0 plus ay times column 0 1. If we carry out the multiplication, we get it is equal to column ax 0 plus column 0 ay, and if we add it, we get column ax ay. The row vector equivalent can be written out in similar manner. One nice thing about the notation of equation 1.28 is that it explicitly contains the basis vectors ux and uy. There is no ambiguity about what basis vectors are. However, the row and column vectors of equation 1.29 and 1.30 do not explicitly reference the basis vector. The reader needs to know what the basis is being used because if the basis changes, the row and column vector change. This is best illustrated with a specific example. If the basis change, the components also change. Therefore, it is important to specify the basis. Let's say that in xy coordinate system, A is equal to 2ux plus 2uy, which is equal to column 2, 2. This vector is displayed graphically in figure 1.2a. You can also express A in the x prime y prime coordinate system, which is rotated from the xy system by 45 degrees as shown in figure 1.2b. In this coordinate system, A is equal to 2 under root 2 ux prime, which is equal to column 2 under root 2 0. If we look at the xy coordinate system, the basis vector for x is 1 0 and the basis vector for y is 0 1. The ax component is 2 and the ay component is 2. Therefore, we will write the column vector as 2 2. On the other hand, if we rotate the xy coordinate system by 45 degrees, we get another coordinate system which is x prime y prime. In this case, the vector is equal to 2 under root 2 and y prime component is 0. Figure 1.2, the vector A represented in A the xy coordinate system, B the x prime y prime coordinate system. As can be seen in figure 1.2, A has not changed. It has the same length and points in the same direction. In equation 1.33 and 1.34, we have merely expressed A using two different basis sets. If we use unit vector notation, there is no ambiguity about what coordinate system we are using. If we use column vector notation, however, there is no indication of what basis we are talking about. If we simply see column 2, how do we know whether it is expressed in xy basis or the x prime y prime basis? From now on, if there is potential for confusion, we will attempt to remove this ambiguity by placing a subscript on the vector to indicate which basis they are being expressed in. Example, we will write these vectors as column 2 in xy coordinate system and column 2 under root 2 0 in x prime y prime coordinate system. The difference between a vector and its representation as a row or column vector is why we are using the symbol equal to dot to mean it's represented by. The vector itself is always the same, that is, it is independent of the representation, but it is represented differently depending upon which basis we use. May Allah bless us all. Thank you for watching. Allah Hafiz.